Hello, welcome. Finally, we are here to serve you everything that you need. Today, we're going to be looking at adiabatic compression of an ideal gas. And this is a very straightforward question from the past questions, and I believe that you need it. So that's why I'm bringing it. It says, an ideal gas at 25 degrees Celsius is continuously compressed adiabatically from a pressure of 2.0 bar to 7 bar pressure. The feed flow rate is 1.0 mole per minute. The heat capacity Cp is constant and equal to 25 joule per mole per Kelvin. What is the temperature of the gas exiting the compressor when the compression is reversible? That's the first case. And second case, when the compression is irreversible and work required is 20% more than the one required for a reversible process at the same exit temperature. To do this, you simply make a diagram of this process. This is the process, this is the inlet gas, and it's moving in at 25 degrees Celsius and pressure of 2 bar. This is the compressor, and it's being compressed to pressure of what? 7 bar, from 2 bar to 7 bar. Second temperature you don't know, and that is what you are told to calculate if the process is reversible. So we are going to use this to calculate. This is the initial temperature, 25. This is the initial pressure, 2 bar. And it's going to a temperature you don't know, which you are told to calculate, and pressure of 7 bar. So, what is the equation that you use for adiabatic compression for a closed system? You use this equation, T2 over T1 is equal to P2 over P1. All to power, this sign, I don't know whether it's gamma or what, minus 1 all over the same gamma. So this, how do you get this? So that you can fix it in this equation. This omega or what, I don't really know, is equal to Cp over Cv, very, very important. And we already know for an ideal gas that Cp is equal to Cv plus R. So, knowing that Cp is equal to this, it means that Cv is equal to Cp minus R. So, bringing it into this equation, this is simply equal to Cp we already know is 25 joules, all over Cv. Cv is the same thing as saying Cp minus R. So it's going to be 25 minus R is 8.314. So if you solve that, you have your R to be 1.5. So having R to be 1.5, substituting into this equation very simply. T2 is what you're looking for. T1 you already know is 25. So converting this 25 to Kelvin temperature is going to be 273 plus 25. P2 is 7, P1 is 2. Then what you already got here is 1.5. So say 1.5 minus 1. All over 1.5. So if you solve this down, you're going to get T2 to be equal to 28 times 3.5 all to power 1 over 3, which will give you 452, and that is the answer. In subsequent class, I'll be showing you how to solve for the second one. This is reversible. For irreversible, that's what I'll be solving next. So that is how you solve this equation. First of all, make this very simple diagram to show you what is coming in. 25 degrees, what is going on, you don't know, that's what you want to calculate. Bar that is coming in, 2 bar, going out, 7 bar. So, make this equation for a closed system, T2 over T1 equal to P2 over P1 to power gamma minus 1 all over gamma. And this gamma is actually equal to Cp over Cv. But we know that Cp is equal to Cv plus R. So, Cv, which you are not given, which you need here is equal to Cp minus R, which is this, Cv minus R. Cp you already know. Solve this down, you get 1.50. Then substitute into this equation, you get this. So that you get your T2 to be 452 Kelvin. And that is how you solve it. Please, if you like this, hit the subscribe button, like, share this, support us in any way that you can. Thank you and God bless you.